Jochen. So recently I developed a couple of web apps, calculators that really aimed at mobile phone. And so the first one I did was for calculating characteristics of a mag loop antenna. And then from there, I was, had a bit of fun, and I thought, what's the next one I can work on? And I did an RF inductor calculator as well. And so in this talk, I'll just sort of talk about how I went through that process and do little demos at the end. So it shouldn't go too long, but yeah, hopefully I can just share a little bit of the fun that I had doing a bit of coding and a little bit of development. So I've been keen on developing a mag loop antenna for a while. So I'm not sure how many of you out there have actually built antennas. I know there's quite a number who sort of have the appeal. So mag loop antennas are also known as small loop antennas, are electrically short. So they have to be compensated with a tuning capacitor. They're very, very narrow band. So they have a high Q, giving them narrow band characteristics. So that's can be a blessing and also, has negative impact. So very narrow band means that you're not going to get you're going to get less interference from other parts of the band. So you've got very high selectivity in selecting the particular frequencies that you're interested in. However, because it's electrically short, radiation resistance is small, and so your signal is going to come through weaker, but hopefully your noise comes in through much weaker. So in constructing a mag loop antenna, you have to be very careful to ensure during construction that you maintain very low DC resistance. So the mag loop antenna in the middle there is a commercially available one, and it uses a coax for the main loop. And then there's a coupling loop in the middle. The one on the right is a do-it-yourself that was constructed by Jerry Ellsworth. It's 2 meters across, but she built it for, I think, 80 and 180 and 160 meter bands. So I believe for 80 meters, there's actually 2 loops. They're wired in parallel to reduce the loop resistance. And then for 160, I believe she has it in series. All right, so components of a mag loop antenna. Most expensive item, well, the most obvious item would be your copper pipe. So Bunnings, you can buy 3/4 inch or 19 millimeter copper pipe. They sell, I think, 18 meter lengths for about $160 from Bunnings. The most expensive, if you're gonna build a mag loop antenna that you're intending to use to transmit significant amounts of power, would be a vacuum variable capacitor. Now you don't need a vacuum variable, but vacuum variables can provide the highest Q, so lowest losses, and you're less likely to get arc over if you're pushing out, more than a few tens of watts. The other component is a coax for a coupling loop, a mounting frame to sort of to affix your antenna on, and then a remote tuning motor. So if you're going to have your antenna away from you, which you should, and you want it to be able to control the frequency from your shack, then most do-it-yourself builders will actually have either a stepper motor, something that can actually tune the vacuum variable capacitor. Now there are a number of mag loop capacitors online. Lots of them are quite good. They generate good numbers. This is one of the more popular ones. If you did a search from 66 Pacific, 66 Pacific, I'm sure you all know, have lots of calculators on that web page. And many of the calculators online are similar, where you punch in a bunch of numbers. So for this one, you enter your conductor circumference, your conductor diameter, so your loop circumference, your conductor diameter, and then the frequency and transmit power you want to use. You hit enter, and it'll calculate a number of parameters for you. And this one even suggests that if the length is good for the frequency you're interested in. Another one from VK1SV. Here again, so this one you enter loop radius this time, number of turns, so it supports multi-turn, number of watts, antenna impedance. So this is a bit weird, because how would you know your antenna impedance up front? You put in your desired frequency, And then the last one there before you hit calculate would be your loop inductance. So now how do you know your loop inductance? Well, there's a link to a loop inductance calculator. So I think this is um, a little bit more unwieldy because it's not that intuitive to get the numbers in that you want. But anyway, you hit calculate and it'll generate a series of numbers. Probably one of the better ones. This is now this is an application you have to install. It's a Windows app by KI6GD. So this is quite good. It's quite logical. You put in your loop circumference, your conductor diameter, operating frequency, your power. These are sorts of things that you can sort of think about readily. Then you select metric or imperial, the shape of your loop, material, so copper, aluminum, and then hit calculate, and it'll generate all those numbers. So your bandwidth, your capacitor value, capacitor voltage, and everything you can see on the right there. So that's quite good. But what I didn't like about this one is that you're now installing an app which is quite old. This one was built in 2003. And every time you install something on your computer, you're essentially putting yourself at risk. You know, you don't know if it's a trusted application, if you don't know if there's going to be any malware in it. So I'd been thinking a while to make my own calculator. And so looking at the other calculators around, I looked at what was good about them and what I wasn't too keen on. So I wasn't too keen on something that you had to install, because I think that puts a barrier. And plus, I'm a bit of a Mac person, so Windows application doesn't really do much for me. Another one, another good one online is Steve Yates. So he built a calculator using Excel. So the one on the right, you can see that's the front page. You punch in, again, numbers, the dimensions of what you're wanting to build, amount of power, and then it'll calculate for that single frequency. And then on the third tab, which is what I've got in the background, he actually calculates a bunch of parameters for a number of frequencies, but they're all like 1, 2, 3, 4 megahertz. So I like that, the idea that he's calculated everything for these frequencies. But to me, they weren't exactly the amateur radio frequencies. So like, 17 megahertz or 13 megahertz. Well, sort of 14.1 to 14.3 weren't really in there. So you'd have to do a little bit of interpolation. But I thought the concept was pretty good. And the numbers that he generates are quite good. So I think this is another pretty popular one. So having looked at it, I said, all right, I'm going to develop my own. So what did I do? First thing I had to do is do a bit of research, find out about the sorts of calculations I had to do. What are the parameters that I wanted to calculate? So I dove in. First book I went to was the Krauss book. So I had that from my uni days, looked up, read everything I could about small loop antennas, backed that up with Balanis. So these two books on antennas are actually quite good up top. Then of course I looked at the ARRL handbook and the ARRL antenna book. And then from there, they sort of referenced sort of research papers. So I dove and found them online and actually did a bit of reading as well. So first one was to this Japanese researcher, Nagaoka. He did stuff on solenoid inductance. So that'd be for multi-turn loops and actually solenoids, and how the geometry, the shape of a solenoid affects the inductance. Medhurst did stuff in the mid-40s, just after World War II. So he did studies on HF resistance and self-capacitance of solenoids. And solenoids are a special case, or are related to magnetic loop antennas. This J.S. Smith, he studied the proximity effect of multi-turn loops. I think his research was in the 70s, and it looks like, a lot of this research is sort of old, but I guess the science doesn't really change. So they knew about the proximity effect and had it all figured out, many, many decades ago. And that last paper, which is more recent one, D.W. Knight, he's actually a professor, a retired professor. He wrote a paper, I think in 2016, that sort of ties it all together. And I found that really useful because he talked about the history of, and went through Nagaoka, Medhurst, Smith, and all others beforehand. And he sort of updated some equations to sort of show what the best and most recent equations would be that sort of matches reality more closely. So this was an interesting one. I'm just presenting this because, so Nagaoka, he studied lots of different solenoids. And if you see the graph on the right there, um, he's looked at the diameter, the length of a single layer coil, and related to the diameter of the coil. So you can see a cross section there. And it looks like for very, very long solenoids, that K factor approaches 1. So, and the theory is that the magnetic flux, there's very little leakage. So you get pretty much all the magnetic flux that's going through the middle, and nothing that's crossing the conductors. And so it produces numbers that are as predicted by theory. But when your solenoids as they get shorter, the predicted results diverge from measured reality. And so he came up with this curve that was actually empirically measured, and it's a correction factor, so that your inductance, the standard inductance equation, produces correct results for very short coils. Another one that I thought was quite important was the studies from this G.S. Smith on proximity effect. So he looked at, up on the right there, you see the skin effect. And so for an AC current traveling through a circular conductor, the field that's set up, the self-induced field by the current that's flowing, tends to push against each other. And so the electrons tend to bunch towards the outside of the conductor. And the higher the frequency, the narrower, the more dense they get close to the edges. And so what happens is actually most of the conductor in the middle doesn't actually pass any RF current. So for DC, current goes through pretty uniformly across the conductor, but as your frequency goes up, the current tends to bunch on the outside. And so actually your AC resistance tends to be higher than your DC resistance. And so, and that's where you sort of get to the microwave frequencies, they become waveguides, and there's no point having a solid conductor that doesn't conduct any current in the middle, because you have all the current bunched up on the outside. And similarly, that if you look down at proximity effect, when you have on the left there, the pair on the left show, if you have two conductors next to each other with currents going in the same direction, same effect sort of happening. The current flow tend to push away from each other, and they bunch up towards the edges. So you don't get much current flowing where the conductors are close to each other. And so you can minimize this, and that would give you the idea of, well, I can actually minimize that effect, improve the Q of my circuit by increasing the spacing in between. The opposite happens if you have the currents going in opposite directions. So, and so this image actually has a mistake. The one on the left, I think, should have 2 pluses or 2 minuses to indicate that the current's going in the same direction. On the right, if the current's going in opposite directions, then they tend to attract each other because the fields are in opposite directions. But similarly, because the current is bunching up and it's not making use of the full cross section of the conductor, your resistance goes up. So my objective then was, I want to take advantage coming up with a modern calculator using like today's technologies. I said, I'm going to target the mobile phone primarily. I want it to be run on any mobile phone. So I wanted to do it, if I did it in a web app using HTML5, JavaScript, and CSS, should be able to run on pretty much any browser and on any platform. Browsers run on, iOS, sort of iPhones and Androids, and they run obviously in every Windows or Mac computer. What I liked, then I thought, slider widgets would be my preference to select what sort of parameters you wanted to calculate. And slider widgets are those buttons, which I'll demonstrate in a minute, that you can just drag using your finger up and down, and that changes the values. And I wanted the application to basically recalculate all parameters of the antenna on the fly as you move your finger. And the idea was to make it intuitive and to give you a sense of how the behavior of the antenna would change as you're changing it. So I wanted that level of interactivity. So if you look, looking back at those initial web pages that you put in a bunch of numbers, you can do one calculation every, maybe 10 seconds if you put in a bunch of numbers. So it doesn't really give you an interactive and an intuitive feel of what's going on. Whereas I thought, well, if you made sliders to say, select the size of your conductor, the size of your loop, then you should get an intuitive feel of how the physics changes when you change the parameters and dimensions of your antenna. So these were the input parameters I decided on. I wanted, for the magloop antenna, I wanted you to be able to first pick the loop diameter. Actually, I've got this opposite around. It's actually the conductor diameter first. So if you were to go to Bunnings, you'd buy, you have what's available, say 19 millimeter wide copper pipe. So that's the first input, which is that phi or psi A. That's the conductor diameter. Next one was, well, the next thing you're going to do is how big is my loop going to be? So that's going to be your loop diameter. So the next thing you actually select then is select your loop diameter. And as you're actually sweeping these, it's going to be actually recalculating everything, all the characteristics. It'll actually be recalculating and predicting the characteristics of the magloop antenna. Next one was, which I actually went on after, once I had it working, was, well, I wanted to look at multi-loop antennas. Now, I realized most people don't actually make multi-loops, and I wanted to sort of, I guess, understand why. That's what the N is. So most of the time people use loop 1, but you can see what would happen if you actually increase the number of loops in the antenna. What I found is actually when you go up, anything more than really 2 loops and the self-inductance, the self-resonant frequency of the magloop goes down into HF frequencies very quickly, to the point that they're actually below the frequencies that you might be interested in. So practically, I think a 1 or 2 loop antenna is I think most practical for the typical sizes. And in those cases where you're using a multi-loop antenna, the C on A there is a spacing ratio. So it's the ratio of the gap, the conductors next to each other divided by the diameter of the conductor. And I'll show that in a minute. And then lastly, I said, well, if you were to transmit a certain amount of power, I wanted to be able to calculate, well, what's the sort of voltages you'd see across the tuning capacitor, so that you could work out if your tuning capacitor, what the limits of the tuning capacitor you have at hand. So if you wanted to punch out 400 watts, you quickly see that you'll have potentially tens of kilovolts, and maybe only vacuum variables can actually handle that. You probably could, air gap capacitors probably couldn't handle large amounts of power. Calculated specifications. So the calculator will calculate the tuning capacitor at that frequency, calculate the capacitor voltage, which is related to the input power, the bandwidth in kilohertz. So you'd find if your Q was too high and maybe you're too narrow for using on SSB, and maybe you'd be stuck really with practically using it for CW. Antenna efficiency. So with magloop antennas, it's not unusual to have antenna efficiencies down in the 1% or less even. So if you wanted to know that you're actually pushing out the power, this would give you an idea of what are the practical sizes compared to the frequencies that you're interested in. Radiation resistance, which tends to be in the milliohms. So I've got there as ohms, but actually it tends to be milliohms, which is obviously very, very low. Loss resistance, which tends to be similar. So if your loss resistance and radiation resistance are the same, then your antenna efficiency is about 50%. Reactance, which is related to the inductance of the antenna at that frequency. Then the quality factor, which I calculate using actually the AC resistance, also taking into account skin effect and proximity effects from multi-loop antennas. And finally, loop current, which again is related to the transmit power. So putting that together, this is the interface I came up with that I'll run on a mobile phone. So here's some screenshots. On the left are all the numbers. Now you can see it's quite cluttered because there's so much info you're actually trying to put onto a graph. You end up looking like actually quite cluttered. So along the x-axis is the frequency, and I'm calculating amateur radio frequencies from, I think, 1.8 megahertz up to 28 megahertz. And then all the different axes which are overlapping. So you have the tuning capacitance, the kilovolts. So that can be actually hard to read when you first look at it and you say, wow, but at least you get an appreciation of the shape. If you can match the colors, you get an appreciation of the shape of how things change over frequency. And noting that black one there, that's the antenna efficiency. And so you can say for this case, antenna efficiency doesn't get past 50% until about maybe 14 megahertz, between 10 and 14 megahertz. I think that's a 1 meter loop. On the right, if you tap in any of those dots in the middle, it'll actually show you in one sort of clean square all the parameters for that particular frequency. So then you can sort of write them down and say, all right, yep, I'm happy with that. And those are the characteristics, or you can screenshot it. If you scroll down on the application, you'll see that there are the sliders down the bottom to select the dimensions. And as you're sliding them, they actually update instantaneously. So with every little movement of the slider, everything gets recalculated. And I think this is what it looks like on a desktop. So a little bit more spread out, a bit more room, a little bit easier to read. And I think what I want to do now is just switch over to a little demo. So I might just have to leave presentation mode for a sec. All right. If I can actually, okay. All right, so this is actually how I was developing, by the way. So on a browser, this is what it looks like on a mobile. And I know, is that pretty small? Can you see that? I'll make it larger in a sec, but I was just showing how it'll look on a mobile if you had it running. So as you change the conductor diameter, you get a visual indicator of what you're actually changing. Changing the loop diameter as I make the loop bigger. I put a cap on the frequency range. So now, say with a 5 meter diameter loop, and I think diameter is a more intuitive measure rather than circumference. So I'm using diameter here. So 1 meter diameter is down here. That's what it looked like. Now let me go to a desktop. So view, which is a bit bigger. All right, so say with that case of using the Bunnings copper pipe, I'll set this to 19 millimeters. You can see now at 1 meter diameter loop, we give you an inductance of 2.54 microhenry. And then it's calculated across the amateur radio frequencies. So following on the left, the tuning capacitor voltage is the green one. So say over here, for that 1 meter loop, to get it to resonate at 3.5 meg or 80 meters, you need 814 picofarads. And as you go up, say at 5 megahertz, which unfortunately we can't transmit on, I think that just got canned last week. I had my fingers crossed. It's going to be about 400 picofarads. Say at 7, it's 200 picofarads. And you'll see this change. Say if I wanted to make I wanted a larger loop that could do lower frequencies better. So say I go up to 3 meters across. All right, and now what do I need for 1.8 meg? I need 800 picofarad. For 3.5 megahertz, now you're down to 200 picofarads. And then you can see if I add coils to my loop and see how things change. Say this is for 4 coils. Now that I have the 4 coils there, I can actually change the spacing ratio, and you get a visual indicator on the right there what's actually happening as you're changing the spacing ratio, and you can see the scales, the prediction update on the fly, and you can actually get a bit of a feel for which way the Q is behaving. So if I reduce the space, if I went to the left, proximity effect kicks in and the Q factor drops. So like the maximum Q now is down to 900. If I keep going left, it's down to about 600, 500. You know, you get those the AC resistance increases as the conductors get closer together. As you get further away, the AC resistance improves, it gets lower, and your Q improves. So that's that purple indicator. So you can use this to get a bit of a, I guess, a feel of how the physics of the antenna change as you change dimensions. And then transmit power here. I guess the only thing that really gets affected is the kilovolts on the axis. So as you go up with transmit power, the KV, the voltage across capacitor increases. And same with the current, the predicted current. If you scroll down as well, I think I explain everything here. I put some notes in to explain what each one is and all the outputs. So yeah, that's the magloop calculator. Is there any questions before I jump to the inductor?
Yeah, Miguel, you've done the calculations for the main loop. I mean, it's absolutely outstanding. What about the driven loop?
Oh, yeah, no, I didn't actually. No, that's not part of this. I just drew a little circle there to indicate that there is a driven loop, but I think people tend to use, I think, 1/5 the diameter of the main loop as a common way of coupling if it was circular. But no, I haven't. Yeah, this calculator doesn't do anything regarding the actual coupling loop. Maybe that's something I need to look into, see if there's anything I can do there.
Well, you are right. Yeah, I think 1/5 is the conventional wisdom.
Yeah.
I've played around with the coupling loop by using aluminium strap, using coax, using solid state wire, solid wire, copper tubing, and it makes a huge difference to the practical efficiency of the antenna, which is why I'd asked, if you'd had to play around with what those parameters, because when you make a loop, and once you decide on what you're going to make the main loop out of, you don't sort of change that too often. But the coupling loop is where you can actually play around. And the other thing that I've read is that people play around with the shape of the coupling loop and turn it into an a sort of ellipse. And so there's a lot in there.
Yeah, absolutely. Yeah, and I have seen that as well, with improving your coupling by flattening it out. And I guess it makes sense because the magnetic field intensity increases as you get closer to the main loop. So if you flatten it off, you're intersecting more of that. But yeah, actually, I mean, I haven't seen any calculators that have done that, and I guess I'm not sure how I would do that. So that's why I haven't done it. But if you see anything that sort of shows, I guess, any sort of way to predict that, I would love that, and I could incorporate it if anyone sees anything. But it's not something I've come across actually.
Miguel, a simple one. 19 mil copper pipe, is that significantly better than, say, the 12 mil, which is the standard copper pipe we use in our houses?
I don't actually. We can try it out. So, I think currently 19 mil. If I drop it to, was it 12 millimeters? Sorry.
House, plumbing your houses and things.
Yeah. Look, I don't think a heck of a lot. It does change it, but yeah. Like, I think, okay, so I'm just looking at the Q. Say I'm getting Qs now here of what, 2,000, say 300. So actually you can go up on it there. Q of, peaks at around what, 2,300 roughly. If I go down to 12 millimeters, Qs down to about 1,700. So there's a little bit of a difference, but I don't know and the other thing I guess is we look at is the efficiency. So say if we're looking at, where's a decent one? Okay, so say for 7 megahertz, almost 2 meter diameter. What are we looking at here? Efficiency is 42%. So if I go up to 19, efficiency is up to 53%. So you'll get a bit of improvement. Resistance will drop a little bit, but I don't think it's that different. But you can get a little bit of an appreciation. Obviously, the bigger would be better, more efficient. But as you get more efficient as well, your Q can get quite high. And if you make it too high, yes, it's going to be efficient, but also it might become unusable for SSB. So I'm predicting here, like, what's the bandwidth? 4.2 kilohertz. That's getting pretty narrow. Normal voice is what, 3 kilohertz, I think, roughly. So you might start getting this distortion. Maybe not at 4 kilohertz, but maybe, maybe at higher Qs.
Well, the reason I asked, Miguel, is obviously that as far as I can see, these antennas are portable, which is one of their benefits.
Yeah.
And, the heavier the bit of copper, the more you have to support it on your bit of PVC pipe.
Well, I was going to say that
supporting the vast is going to be a problem.
The vast majority of commercially available magnetic loops, the alpha loop, the Alex loop, they use LMR 400 or equivalent in coax, use copper. Okay, so but the difference is that the manufacturers appear to be divided, and some of them they'll join the inner and outer together, short out. Then some will only run the inner, and some will only run the outer, and they all swear this is the best one. And I've tried between those three combinations. So, but it's a bit of fun trying, a bit of soldering.
Yeah, it'd be good to experiment. Yeah. But I guess the copper ones would be more for people who are going to have a fixed site at their home, right? I guess it's not going to be obviously as portable as those coax ones that you can buy. All right. Okay, I suppose I'll jump on to the next one, which is so out of that, I quite had a bit of fun on there, and I thought, well, what could be the next project, and what would be useful for me? And I guess, all right, let me just maximize this. I wanted to do an RF inductor calculator. I thought this was an area that it might not be as intuitive, so I thought it'd be nice to actually have a calculator that can sort of improve my intuition for inductors at RF frequencies. So I wanted to leverage my work from the stuff I had done with the mag loop calculator, and I wanted to do the basics of calculating the parameters for a single layer solenoid style coil, like you see up there. And then you again use the slider to give you a sort of intuitive feel of how the characteristics change and what's the sort of values you can get quickly. Because I think that interactive thing is really what's made my calculator different from most calculators out there. Taking advantage of the mobile phone's power in your hand and that sort of tactile, as I'm changing it, it's recalculating on the fly. And so you can get that intuition, and hopefully that makes us all, sort of better experimenters. So again, I leveraged, leaned on Knight's 2016 paper, which, I used to get equations for the self-capacitance formula and self-resonance of a coil. So a lot of formulas are available from more basic formulas from ARRL and stuff, but they didn't provide some of the more advanced sort of self-capacitance and self-resonance, and this paper really covered it pretty well. Also, I leveraged the papers I had read on proximity effect, and so how that sort of gets factored in. So here's a screenshot of my first crack at it. Actually, this is already after a few goes, but because I haven't saved any of the earlier stuff. But it was my initial metric wire, and this is one of the things I actually learned was after doing this, that actually there's no such thing as metric wire. It seems like all wire is like either AWG or SWG. I just assumed from JCAR, when you can buy 0.8 millimeter wire or 1 millimeter wire, 1.25, I'm thinking, oh yeah, those are standard metric sizes, and I never sort of thought beyond that. So I thought that was the basic size. But actually, once I did this and I sent it off to some ham groups, they were asking, oh, are you going to do one for AWG and for SWG? And then I looked into it and I thought, actually, that's what I should have started off with. But anyway, so the wire diameter is that psi alpha The next one is the loop diameter. So I've sort of followed the convention, and this is the same sort of symbology they use in textbooks. Next one is spacing ratio. Again, the spacing ratio affects the proximity effect, which affects your AC resistance, which obviously affects your Q. Number of turns to select if you want a longer, number of turns, which obviously affects your inductance and the length of your coil. And a desired frequency. So you've only got 5 things to input, and it'll recalculate everything for you. Now, on the left, top left, are the frequency independent values. So values that don't depend on your desired frequency. So, like the inductance of the coil is dependent purely on the geometry of the coil, size of the coil. Same with the static capacitance. Same with the DC resistance of the coil. Now this assumes copper. SRF is your self-resonant frequency. And then wire is denoting the length of the coil, length of the wire you need to wind the coil. And then on the top right, it's sort of saying, well, if you pick a frequency at 7 megahertz, now the reactance of that coil at 7 megahertz will be 72 ohms. The dynamic impedance would be 72.2 ohms. It's a little bit bigger. They seem in this example to be similar. Where that becomes quite different is when you start approaching the self-resonant frequency. And what you'll find is that the impedance becomes very high, because effectively it becomes like a tank circuit close to resonance, which theoretically is sort of infinite resistance. But this does factor in real values for resistance. The next one that looks like a little delta, that's 25 micrometers. That's the skin depth. And then there's the AC resistance. So this differs a little bit from the DC resistance because of the skin depth and proximity. And then Q, which is calculated from reactance and the AC resistance. So here are other screenshots. Now, after doing the metric version, I then found out about, oh wow, actually all wires seem to be AWG or SWG. So I created a version for that. Now, when you slide the conductor diameter, they go up and down in levels of in different wire gauges, and then it prints out for our American friends imperial units. But I put the metric units in brackets, because then I figured even for us it's going to be metric. Actually, I realized after. And the SWG looks the same as the AWG, except the numbers are a little bit different because the wire gauges aren't one-to-one correspondence. On the right there, actually, somebody had asked, how about for bigger coils? So I did one that can where the ranges for the conductor diameter and diameter of the coil is larger, say if you're doing choking like balance. And then so I gave indicators, well, this would be sort of coax. Now, numbers on this, I'm not 100% sure, because my model still assumes that you're using solid conductor. Obviously, coax doesn't use solid conductor. It's going to be mostly dielectric. But it should give you a bit of a feel for what's going on. I compared it to empirical figures, and on some cases was order of magnitude of 2. So it was like I think it was predicting numbers that were, the self-resonant frequency might have been double of what was measured. So that one might need a little bit of improvement. Once I get a VNA, I'll actually be able to get the figures myself, and then I can adjust it accordingly. So I was just going to demo that. So this is what it looks like on a mobile phone, metric version. As you sort of sweep the diameter size, it'll show in the middle what it's closest to in the wire gauge, and change numbers accordingly. If I go to AWG, now it's going to actually change according to American wire gauge. So say if we go to 22 AWG, now you want to wind on, say, on a 30 millimeter former. So over here is the inner and outer diameter. which is essentially, and this is the mean diameter. So the B value gives you the mean diameter of, which is the middle of the conductor, and these figures here are subtracting the conductor's dimension. So the I is for the inner diameter and O is outer diameter. So it's producing everything you need, and you just look at which one is important to you. And now I can change the spacing ratio, and you can see at the top left there what the inductance is and what the impedances in the top right are. If I want to make more windings, what the effective on your impedance is going to be. And if I want to use this, say, at 14 megahertz, okay, so I'll be at 14. So say in this coil that I've just done, its self-resonant frequency is 44. If I wanted to get it lower, then I can say increase the diameter of the conductor, maybe play around with this. Oh yeah, I can, if I wind it a little bit more tightly, the self-resonant frequency goes down, but I can see also the Q factor in the top right there goes down as well. So I can, I can sort of tune what I'm happy with, maybe make this a little bit bigger. And now you can, with these larger values, you can start seeing there's a divergence. So the reactance might be almost 3 kilo ohms. Now the impedance is actually 5 kilo ohms, because you're starting to get your desired frequency close to the self-resonant frequency of the coil. So the impedance actually goes up. And this is actually important when you're doing, say, using coax, and you wanted to use a, you're interested in choking impedance. So say RG58, I will increase the diameter to say 250 millimeters. And here I've got 10 turns. So now I'm seeing 8 kilo ohms of choking impedance on your common mode. So, that's quite high. That should provide you with decent sort of choking. If you might do better, even higher for end-fed antennas. End-fed antennas feed point impedance might be, say, 2.4 kilo ohms. So if you want to go 10 times higher than that, you'd be looking for 24 kilo ohms. The only way you can get up there would be to get close to the self-resonant frequency of the choke. So say I increase this, sorry, a couple more turns, we'll get it close. So now self-resonant 7.1 meg. I'm interested in 7 meg. Wow, I'm now getting a choking impedance of almost 96 kilo ohms, which is very high. It gets very close to self-resonance at that spacing, and then you can play around with your spacing, see how things change. This one isn't as well set up for, I still have to fix the layout for this for the desktop, because it's really been designed for mobiles. But yeah, on the desktop, if you want to see it bigger, the sliders are up here. And I think that's pretty much it. Last slide was just the links, if you're interested. And I guess the next project that I'm looking at doing now, I was thinking would be somewhere I wanted to improve my knowledge on is toroid calculator. So something where you can actually pick the material type for a ferrite, say type 31, 43, 52, the sort of common amateur radio materials for ferrites, and also maybe later on make a version for powdered iron materials. And then based on the size of the toroid you have, you can play around with the turns of the primary and secondary, say if you're doing a broadband transformer, or if you were wanting to use it as an inductor or calculate for common mode impedance, say for chokes, do the same sort of idea of using sliders to give you, calculate those sorts of things for you. And that's it. Any questions?
Any questions?
Well done. Well done.
Miguel, you mentioned wire gauge. Just for our own education, I knew that American wire AWGs have been around forever. Are you saying that when JK say it's 1 millimeter, it's not, it's just the closest AWG size to 1 millimeter? Is that what they're doing?
I think so. I think so, because I spent a fair bit of time trying to look and Googling metric wire gauges, and I'm like, how can there not be metric wire gauges? I mean, and I guess to me, anyway, at least my understanding now is it feels like the whole world's just used the AWG or SWG. So I didn't even know about SWG rig different. I always thought they were the same thing until some Indian guy actually on one of the forums asked me, can you do a version for an SWG? And I said, SWG, what's that? And so I Googled it and I said, oh, right, actually they're not exactly the same. So SWG is the standard wire gauge, and that's sort of British Empire stuff. And of course, the Americans have to be different. So they got their AWG. And I think it's, the industry globally is essentially using those as standards. And even though they might publish the diameter in metric, I think it's still based off those. That's my understanding. Happy to be proven wrong, but just from my Googling, that seems to be what's my understanding anyway.
I believe you, Miguel. I mean, we go to Bunnings and buy timber. It's labelled in metric, but it's not metric. Nothing's metric in timber.
Yeah.
So the lengths are cut to meters, but the diameters are all inches. Everything's in inches. In 2020, everything's still in inches. But Australian requires them to label it in millimeters. They do, but it's not. Copper pipe, 19 mil. Where'd that come from? It's 3/4 of an inch. We all know that. It's an old
that's right. Yeah.
Around, and it's never metric. It's just labelled as 19 mil, that copper pipe. It's actually 3/4. And so the more you get involved with engineering, all sorts of engineering, discover that everything's just based on the nearest metric equivalent to an imperial size, which presumably around the world, it's still the standard. Imperial sizes are still a guide around the world. Don't know about Germany or somewhere like Switzerland, but the rest of us, it's all imperial, really.
Yeah.
Check it. Everything based on imperial.
And funny thing is, actually, I was watching something the other night, and even in the US standard at the National Institute of Science and Technology is actually metric. And so all imperial measurements are actually derived from a metric standard. So even though in the US everyone learns inches and all that, actually they're based on the standard metric, which has come out of Paris. So US actually at the standards level is metric, and all imperial units are actually conversions from a metric unit, which blew my mind. So, anyway.
Any other questions?
Have you tried this on Android Studio?
What do you, sorry, no. I mean, it should run on Android because it's just going to be a browser. So it should just work.
Developer options and the Chrome browser.
Yeah. So I'm using a Chrome browser for my development. And it's got a good development environment. So it's been handy. That's how I've developed it. And they have simulators for mobile phones. So that's been very useful. So before I've pushed it up to a web server that you can actually try it on a mobile, I get it working on the Chrome browser first.
Well, on behalf of everyone, Miguel, I mean, heartiest congratulations. It's an outstanding piece of work. When I first saw it a couple of months ago, I plugged in all of the loops that I've been playing with that I built just to see
how close they were.
to see why they didn't work. And of course, it proved why they didn't work. And you said, you talked about toroids. I brought along tonight my newest little ATU that I just built, and there's 5 little toroids that I wound meticulously in there with absolutely no idea how many windings. And I about what was going to end up in terms of inductors. So wait with bated breath to see the new one. It'll be outstanding.
Jeff, I was going to ask you, how did your unit go? Now you've seen all the theory and you built it.
Put it away again. The theory will prove that it doesn't work.
You told me last week.
Yeah, well, no, thanks very much. That's absolutely
That's
outstanding.
fantastic, Miguel. Got a great tool.
Yeah.
So, Miguel,
Thanks, guys.
you made that available as a link on the web, or what? Sorry,
absolutely. So I think I put one of them up. So yeah, I'll put them up on the web. I've sent it to Martin, so Martin can probably forward it to you as well.
The links, yeah.
But yeah, I'll or maybe I'm not sure where best to put it up on Facebook. Martin, maybe if you can
Work on Firefox too.
Just send it to the Peels.
To the mailing list.
to the mailing list. Yeah, okay. All right. Happy to do that.
Yeah, it's great.
And it will end up on the website anyway, when she's editing.
Can we charge for it?
And well presented too, Miguel. You present, I think you present a technical topic very well.
All right. Thanks. Thanks, Paul.
So, Miguel, have you got a couple of minutes?
Yeah, sure.
Yeah.
I'm actually going to, I'll mute the meeting. There you go. I'll mute the meeting so that we can continue talking.
Okay, cool. Can they hear us?
Oh, yeah, they can hear us, but that's all right.
Okay.
We won't say anything about them. So if I understand, you did the research by looking at those papers, and you settled on the Knight paper as the sort of, it brought most of the information together.
I think, yeah, yeah. I mean, some of the other equations were out of AWL, but sort of self-resonant frequency, that seemed to be the one that was, and capacitance is derived based on self-resonant frequency. So it's like,
Yep.
It's not like you get, okay, calculate inductance, calculate the capacitance, then you use that to find your self-resonant. Actually, there's a better model by calculating inductance, which is sort of straightforward. It's well known and it's predictable. And
Yep.
then there's a way to calculate your self-resonant frequency. And from that, you can work out what the effective
What the
capacitance
capacitor,
is.
yeah.
Yeah,
Yep.
so it's sort of asked about.
Yeah. Oh, beautiful. So, okay, then having I guess the formula that you're going to use.
Yeah.
So what did you then write? Yeah, I guess what language did you write it in, or where does it sit?
Yep. In fact, I'll just bring it up. I will share my screen. Okay, share. All right. Let me know if you can see.
Yeah, no, that's beautiful.
Okay, so
so what is that?
Okay, so this is the MagLoop calculator code, which is essentially is the HTML piece.
Yep.
So
and how did you generate that?
Oh, that's hand coded. So I coded that.
Really?
By hand, yeah.
Hand-coded.
Yeah. So these are over here. Okay, it describes the top of the page, and I've got my link. This bit here, these are the different sliders.
Yep.
So you can see the class sliders, and then that's Unicode for that symbol. So it was fun finding different Unicode symbols.
Yeah.
So that's the conductor diameter. This is the slider for the loop diameter, and then number of turns, spacing ratio, and then transmit power. And if you go down, these are the sort of the notes that show up at the bottom of the page. And then that's essentially all the HTML. Most of the HTML stops there. Now the next bit is the script, which is in JavaScript. So this is where all the grunt work happens. So the MagLoop uses an external library, a charting library. So that main chart is actually a third-party library I use.
Right. Okay. Yep. Okay.
Right.
So it calls, it goes out and calls on that, and that information then comes back as what, SRC, right? Or
yeah. So I guess the next bit here, these are connections, my links from the sliders into the actual bulk of the calculations. So here's all the JavaScript now. Like say here, these are the ham frequencies I'm using.
Yeah.
So in megahertz, so 1.8, 3.5 is just in a list, and you can actually add more if you want, and then just regenerate the page, and it'll just put more dots on the screen. This is the function for calculating the inductance. So you know, I essentially get the coil radius, conductor radius, number of turns, blah, and then here is the sort of equation to solve for inductance. And so it's just based on basic geometry. So that one's quite a simple one.
Yeah.
Radiation resistance as well is not huge, but it's compound, so that's there to
So
calculate the radiation.
So the radiation
Yeah.
resistance, the actual calculation is number of
Yeah,
turns times 2 times K.
K, which is
Yeah.
no, which is this constant up here, sorry. Yeah,
Right.
and then the ratio to the power of 4,
Right.
and then I return that.
So with constant K, what's the math? MATH? Is that a
Oh,
is
that's
that a
that's a
variable?
math library. So I'm saying pi. Get the number pi from that math library. So
I see.
math.pi
Right,
is just,
okay.
it's just a
Right.
constant pi. Yep. So this is how this returns the radiation resistance for one frequency.
Yep.
One frequency, and then this next one here, calculate, essentially goes through all the frequencies that I'm interested in. So
Yep.
this function calls that, says, all right, what are all those list of
Yep.
frequencies, and solve it for each one. And
Yep.
it's a bunch of those. So those are the simple stuff. It gets more complicated down here. This is Nagaoka to generate that sort of curve.
Yep.
And that gets used in here. This is that stuff I got out of Night, essentially, for the multi-loop capacitance piece. Proximity resistance is actually empirical, so it's not calculated, it's interpolated. So I essentially got the empirical tables that were measured empirically from, well, not quite 100 years ago, but a long time ago. And these are still valid today. And so these are for up to 8 turns. So on the left there, you have 1 to 8 turns. And then on the right is the spacing ratio. So then it essentially interpolates the values from a lookup table. And similar, so these are all the different functions. And then I think when you get down to the end, there's a couple of drawing functions which draw the little screens. So every, and write the text. So that's all here. So that's just grunt work, working out loops and points and then drawing it. And then text, these are where I'm actually punching out transmit power, inductance, and all that into that graphic. Yep. And then the last one is a charting. Down the bottom is the charting tool. So it's actually one big function. Once I've solved everything, I pass it to this charting things for it to draw it for me. Yep. And so that's it. But so it's combination of HTML, JavaScript, and then here's the CSS, which is the cascading style sheet, which is how you decorate the look of your app. So that
Okay. Wow. Well, that's fantastic. Thank you for that. That's you did it by hand. How good is that?
Obviously, I'm a sucker for torture. No, it's fun.
How long has it taken you to
it wasn't that long. I think, I watched a lot of YouTube videos to learn actually how to code up web apps properly, and actually forced myself to learn a little bit of CSS, at least enough to do the app. And then, so there's actually a lot of YouTube out there that can help get you going. And then once you have something, the basics working, and then it becomes easy to iterate and so once I have the basic drawing working and I've got the canvas working and I can draw something, and then it becomes easy to actually work out what I want to draw, and then make a change, see what it looks like, make a change, see what it looks like, make a change, see what it looks like. Eventually you run out of changes to make, and then I think, oh yeah, this is about done.
Now what?
Now I want feedback. Now I'll send to some people and say, hey, what do you reckon?
Yeah.
Can you give me some feedback? Is there something I'm missing and all that? So
it's brilliant. Thank you. I did have one more question, I guess along the same sort of lines. You've got it hosted on your
GitHub.
own server, or
no? It's on GitHub. So that's
on GitHub. Okay.
Yeah. So okay. Share the screen again, and these are the links. So it's coming through.
Yep.
There we
Oh,
go.
I see. Okay.
Yep.
So is that a subscription?
No, so it's actually, if I want to look for somewhere free that I could put it up. So GitHub is it's essentially a website for people to develop open source software.
Yeah.
And there's an option that you can actually serve the files that you've got in there so that they're available for other people. So as long as you're using it for open source, then it's free. I think there's a paid version if you wanted to use their services but not publish it. So it attracts, GitHub's very popular for sort of, open source community.
Okay. Oh, fantastic. All right. Well, that, as Jeff said, that was just a brilliant presentation and fantastic work. So
Yeah, thank you. Appreciate
thank you.
that.